Hello and good afternoon, everybody. We will start or continue today with our introduction in engineer's petrology, and there we will continue with point number 3 from our PowerPoint. That is the so-called magmatic differentiation, and therefore we are using the textbook example, the so-called Bowen's reaction series. So the Bowen's reaction series can actually not find very often in nature, because in nature we are dealing with multiple processes. But on this diagram we have a lot of useful information. So we have here on the y-axis on the left side a temperature scale ranging between 1200 degrees Celsius and 600 degrees Celsius. So, and very on the right hand on this column we have the magma composition at these certain temperatures. So, and then we can see at high temperatures like at 1200 degrees Celsius, we are forming an ultramafic magma which has a very low silica concentration. Then later on at slightly lower temperatures we are forming mafic magma or a basaltic magma. And the mafic or a basaltic rock, you know this by now, that is a gabbro or a basalt, yeah? So then at slightly lower temperatures, maybe at around 900 degrees Celsius, we are forming an intermediate magma which is maybe of the composition of an andesitic magma. That means we are expecting higher silica concentration at around 55%, plus minus 5, yeah. Whereas a ultramafic magma is silica undersaturated and has maybe 48%. So, and finally at lower temperatures, ranging, let us say, between 800 and 600 degrees Celsius, we are forming then a felsic magma, and a felsic magma has a high silica saturation or concentration, can have up to 73% of SiO2, and such a felsic magma forms then a granitic rock, or when we are talking about a volcanic equivalent, then we have a rhyolitic rock, yeah, or a rhyolitic melt. So, and at these different temperatures we are forming then also different minerals. So the prominent mineral in an ultramafic rock, which is a silica undersaturated rock, that is then an olivine, for example, yeah. So, and when we are looking at the feldspars occurring in such a silica undersaturated rock, then we have here calcium-rich plagioclase feldspars, yeah, which are anortites, and these anortites are formed at high temperature conditions. So then when we are going down to the mafic basalt, we have here then another prominent mineral, and this is the mineral pyroxene. And pyroxenes are forming then at lower temperatures, and the chemical composition of your plagioclase is then less calcium rich, but it is still calcium rich, but it has more sodium inside. So then when we are going down to temperatures below 800 degrees Celsius, then we are forming then hydrous minerals, and this in the intermediate andesitic rocks. For example, we are forming then the hydrous mineral, the so-called amphibole, yeah. And the amphibole, you know this, has an OH2 group. And hydrous minerals we are forming at lower temperatures when we are enriching water in the residual melt of our magma chamber, yeah? And our plagioclases becoming then also more enriched in sodium. So at temperatures here, when we are looking at this diagram, let us say lower than 750 degrees Celsius, we are forming then a biotite mica together with a sodium-rich plagioclase. And if you are reaching then temperatures at around 600 degrees Celsius, we have then a rock which contains we are forming a rock with a high silica concentration, that means of felsic composition. And this granitic rock contains then quartz, muscovite mica, and autoclase feldspar. I think that should be clear. So now we are going to the next slide, yeah? And we have just a repeat, we are just repeating some things. We have here, as the temperature decrease from our magma, we are forming then different rock types, and these rock types are then more rich in silica. So, and all these minerals, or here it is called materials, will crystallize in an ordered series. So we have certain minerals which are forming at higher temperatures or crystallizing at higher temperatures, and other minerals are crystallizing at lower temperatures. So, and when we have our plagioclase feldspars, and at high temperatures we are forming a calcium-rich plagioclase, whereas at lower temperatures we are expecting more sodium-rich plagioclases. So, and the composition of our original parental magma, which is of ultramafic composition, will change from ultramafic to andesitic composition, and finally to a felsic rhyolitic composition. So, and here we have the next point, the magmatic differentiation, and here we are talking from the system granite and basalt. So we have here two magma chambers. We have magma chamber A, and in this magma chamber A, we are crystallizing minerals. And then we have a magma chamber B, here in red, and that is a magma chamber where we have a basaltic magma. So that means in magma chamber B, we are expecting a magma which is less silica, which has a lower silica concentration compared to this magma in chamber A. So, and then we have also in the surrounding area partial melting of the country rocks. So, and when we are talking about partial melting, that means a partial melting creates magmas of a particular composition. So, and yes, that is the additional information here. So, and while our magma is cooling, then that means we are forming minerals due to crystallization, and these crystallizing minerals will become settled somewhere in a magma chamber. So that means more heavy minerals will sink to the ground, to the magma chamber. Then more light minerals, they will just float up at the top of the magma chamber. So then, while crystallization has proceeded, we have, or in the next pictures, we have then the connections of magma chamber B and magma chamber A. So we have a mixing of the two magmas will occur, and therefore we are changing then the chemical composition in magma chamber A. So, and as it is written here, a basaltic magma chamber breaks through, that we have then here at this stage, yeah. So, and then we have the influx of basaltic magma into let us say granitic magma. So, and this mixing of these two magmas will result in the formation of an andesitic magma, yeah? So that means the silica saturated magma will get a lower silica concentration, and the basaltic, but the silica concentration will be higher as in the basaltic magma due to these mixing effects. So, and then these crystals which you are crystallizing out will maybe accumulate on the side and roof of the chamber due to the turbulence which is created by the influx of the melt from the basaltic magma chamber. So here we have again some short questions for this chapter, and these short questions you should then answer during your homework, because these chapters are part of the practical. So question number 1, what observation would show that a pluton solidified during fractional crystallization? That was just one question, so that is not too much. So then we have point number 4, we will discuss now forms of igneous intrusions. So we have plutons, we have discordant intrusions, which is a pluton, we have then batholiths, yeah, we have stocks, and we have concordant intrusions. And concordant intrusions are sills, dikes, and veins. So here we have then a nice picture, and on this picture we can then figure out where this different intrusion, which I have just told you right now, where they are related to on this diagram. So we have here on the right hand, we have on the left hand we have the country rock. Then we have here a volcano, and the volcano is an extrusive intrusion. Then we have here some stocks. We have here a dike. We have here a sill. Here we have another sill. Here we have another sill. Then here we have a dike, and here beneath we have a pluton here, yes, and there beneath we have the huge batholite, yeah. So, and here on the top we have a volcanic neck with radiating dikes, and such a volcanic neck looks like a thumb, yeah. So, and these dikes, they are cutting across layers of the country rocks, yeah? These are the dikes. And the sills, they are running parallel to them. So, and finally, the batholiths are the largest forms of plutons, and they can cover at least 100 square kilometers. So here we have another nice picture. We have the rising magma wedges open and fractures the overlying country rocks, yeah? That we have here. So and these overlying rock units maybe will become bow up, as you can see here in this picture, yeah? And the magma melts the surrounding country rock, yeah? And there we are talking then about contact metamorphism. So, and that is the thing, metamorphic petrology and igneous petrology is very, very close to each other. So, and then on our last pictures, and on our last picture on the right hand, we have then the melted country rock, and that mixes the magma and changes its chemical composition. So because pieces from the country rock, they will become then molded, they will fall into your hot melt, then they will become completely molten, and then it will change the chemical composition. So, and another thing which happens, the magma also breaks off blocks of overlying rocks, and these rocks we are calling then xenolites, that sink into the magma and will melt. We are coming now to point 5, igneous processes and plate tectonics. So therefore we are talking about magma factories, and magma factories, these are locations where we are producing a lot of magma, and the biggest magma producer worldwide, is the Middle Ocean Ridge system. So in the Middle Ocean Ridge system, that is a spreading center. You know this by now. So then we have the another magma factory, a large magma factory that is at the subduction zones. And we have the mantle plumes. So now we have here a couple of another few pictures, very, very nice and helpful pictures. We have here the ocean-ocean convergence. That means we have here the collision between one oceanic plate and another oceanic plate. And that happens there in subduction zones when one oceanic lithosphere becomes subducted beneath another oceanic lithosphere, and the product is then you have the formation of Iceland arc volcanoes above the subduction zone. Then and that is, you have here then, for example, in this picture below, you have an Iceland arc volcano which occurs here in Java in Indonesia. So then you have here the spreading center that is then at the Middle Ocean ridges. And there you are producing basaltic intrusivas and basaltic extrusivas. I forgot to mention what type of rock you are producing in the ocean-ocean convergence. You are producing the mafic to intermediate intrusivas, this is plutonism, and mafic to intermediate extrusivas, which is related to volcanism. So at the spreading centers you have basaltic intrusivas and basaltic extrusivas. But you have there also the formation of gabbros, and you have there the rising up from magma, and that will lead to the formation of the two plates moving apart from each other. And in the picture below, we are sitting here on the spreading center of the Middle Ocean Ridge, and that is here the spreading center, which you can see at the surface in Iceland. Yeah. So the next magma producer here, that is the hotspot, and the most famous hotspot chain, that is that one in Hawaii. So that means that you have a mantle plume, and this mantle plume is the hotspot, is sitting somewhere in the mantle while the overlying crust is moving. You will then produce a volcanic chain, and there you have basaltic intrusivas and basaltic extrusivas. And as I told you before, the most famous hotspot volcanoes, these are the Hawaiian volcanic chain. So, and in our last slide, here very on the right hand, we have an ocean-continent convergence. There we have the subduction of an oceanic crust beneath a continental crust, like it is in the western part of North America and South America. And there you have this subduction of oceanic lithosphere beneath a continental lithosphere. And you will form their mafic to intermediate intrusives and mafic to intermediate extrusives. And here in the picture below we have a continental margin volcano, and that is Mount Rainier in Washington, D.C. So these are some different locations where igneous processes are occurring and where they are related to plate tectonic movements. Here again we have here the ocean-ocean convergence, that is the subduction of an oceanic lithosphere beneath another oceanic lithosphere, and you will produce an Iceland arc volcano above the subducted slab. And the products are mafic to intermediate intrusivas and extrusivas. Then at the spreading centers you will form basaltic intrusivas and basaltic extrusivas. Their partial melting will occur in the upper mantle, then you have rising up of magma, and that will lead or will cause the movement from the two oceanic plates apart from each other. Yeah, and as I told you before, these spreading centers, these are the biggest magma producer on this planet. An example below for the oceanic convergence, we have at the Iceland arc volcanoes in Java, for example, but you have them also in Japan and so on. And here for the Middle Ocean ridges, you have the spreading center at the Middle Atlantic Ocean ridge, and in Iceland it is above the sea level, and then you can observe it very easily. So then here we have again the hotspot chain. There we are producing basaltic intrusivas and basaltic extrusivas. We have the movement of the oceanic lithosphere above, and the mantle below is always stationary, and then you will produce a volcanic chain. At the end here from these four slides we have the ocean-continent convergence zone, as you can find it in the western part of North America and as well as in the southern part of North America. There you have the formation of the Andes, yeah. So, and there we have the subduction of an oceanic lithosphere beneath a continental lithosphere, and you will produce mafic to intermediate intrusivas and mafic to intermediate extrusivas. So then we have the next point, which falls under point number 5, igneous processes and plate tectonics. So we have then the origin of magmas in magma factories. So therefore in the middle ocean ridges or in the spreading centers, we have the decompression melting in such spreading centers. So and then we have another type, that is the fluid induced melting in subduction zones. Here for example we are talking about the decompression melting in spreading centers. So we have here at the top, we have newer, very thin sediments. At the middle, at the spreading center, we have at the top here pillow lavas. We have the formation of pillow lavas there because the melt cools down very fast due to the contact with oceanic water, and therefore you are forming that pillows. So and below the pillow lavas you have then the sheeted dikes in basalts, yeah, that is in the upper 2 kilometer. So then below we have about a layer or a gabbro, a layer consisting of gabbro. The gabbro has chemically the same composition as the basalt, but the basalt cooled down much more faster, so then it is more fine grained, and the gabbro had more time to cool down, and therefore the gabbro is more coarse grained, yeah. So and below the gabbro we have then the moho, that is a seismic boundary. And below the moho we have then a layer consisting of peridotite, and below the peridotite we have then our mantle. So we have here the rise up of magma from the mantle, and this rise up of magma from the mantle will then lead or will then cause the formation of a magma chamber by decompression within this gabbroic unit. So and here we have the whole thing again in simple words. Hot mantle rises, decompresses and melts. That is the situation here, and then we have the emplacement of such a magma chamber. So then we have the eruption of a thin dike, and that will cause the spilling of lavas into pillows. So and therefore we have here the dikes, and we have the emplacement of dikes which are intruding in another dikes. So and that causes then dikes intrude into dikes to form the sheeted dike complex above this unit, which consists of gabbro. So and then of course we have the deposition of sediments on the spreading sea floor. And here we have then also the metamorphism, and this were the type of metamorphism which we can observe here. That is a contact metamorphism, and this contact metamorphism will take place in the contact from the gabbro and the magma. So, and here we have then also the influx of cold seawater in the sheeted dye complex, and therefore we will heaten up this seawater, and this seawater carrying then a lot of dissolved minerals. So, and therefore we have the formation of seawater, or not the formation of seawater, but the seawater filters through the basalt layer where it is heated. So when the heated seawater then rises, dissolved minerals precipitate in the ocean. So in your magma chamber you have then also, or in your magma chamber, crystallization will take place. So and this crystallization of minerals will take place, and these minerals depends if they are heavier than the surrounding melt. If they are heavier than the surrounding melt, then they will just sink to the ground and forming there the layer of peridotites. So, and that means then crystals settle out of the magma and forming the peridotite layer. So then we have the next picture here. We have, that was before now, the formation of melt at the spreading centers. Here we are talking now about the fluid-induced melting in subduction zones. So we have here a typical cross-section through a subduction zone. We have here the trench. Then we have here the magma chamber, which rises up above the subduction zones. We are subducting oceanic sediments. And below the oceanic sediments we have an oceanic crust basalt. There below we have an oceanic mantle lithosphere, and there below we have the asthenosphere. So, and this subducting oceanic crust, of course, carries then sediments with, and these sediments are overlying the oceanic crust basalt. So, and between all these sediment grains we have a lot of water, yeah? Of course, these sediments are all very, very wet. So, and this water remains trapped at the pressure and temperature increases. So, I mean, while we are increasing the pressure and the temperature, your mineral grains will become cemented together, and then this water becomes then removed from your former sediment. So it is, but in nature it is not that easy, because at first you are forming hydrous minerals, and these hydrous minerals will then dehydrate, and then you have the formation of dehydration reactions, and these dehydration reactions are causing then the formation of melt in a subduction zone. So, and here we have another picture. The trapped water is released at the temperature increases. So, and I see now that the frame or the recording frame is a little bit smaller than all the letters which are written there. But I have uploaded the PowerPoint on Moodle, and then you can download the complete PowerPoint. You can sit together with your PowerPoint and with the recording, and then you have everything. So, and this release of water will cause the sedimentary rocks to melt at lower temperatures. So that is as I told you before, in principle it is correct, but not in nature. But we will discuss the formation of melt in the subduction zone more in detail. But for now it is good to know for you that is caused by the release of water. So, and the water and the molten sediments melt parts of the overlying plate, as it is here. And I mean, this melt has a lower density as the surrounding area and will then rise up at the bottom of your overlying oceanic lithosphere or of the overlying continental lithosphere, and there we can then cause the formation of a pluton or of a volcanic rock. So you have then the formation of extrusivas or intrusivas above your subduction zone. So, and that is written here, the molten sediments combine then with the lithospheric magma. So, and the magma of intermediate composition is erupted to form arc volcanoes. So then I have here another some other short questions for this chapter, and we will just go through. So if you were to drill a hole through the crust of a mid-ocean ridge, what intrusive or extrusive igneous rocks might you expect to encounter at or near the surface? What intrusive or extrusive igneous rocks might you expect at the base of the crust? So this question is actually easy to answer. You just have to go through your slides and watching it, and then you can answering it, and that's all. Water is abundant in sedimentary rocks and oceanic crust of subduction zones. How would the water affect melting in these zones? You should by now also able to answer these questions. Just check your figures again and check everything what I told you during class. So last question, I think so. Why are granitic and andesitic rocks so plentiful? Now we are coming to the key terms and concepts. So we talked about the andesites and the formation of the andesites. We talked also about the basalts and the formation of basalts. Then we discussed also the occurrence and the location of the batholiths, of the bombs, I mean the volcanic bombs. We talked about concordant intrusions. We talked about country rocks. I told you also what a dacite is, what is meant by decompression melting. I showed you also the picture where dikes occur and what dikes are. I showed you also what discordant intrusions are. We discussed also the formation of extrusive rocks, of felsic rocks. I told you also about fluid-induced melting, about fractional crystallization, and about gabbros, yeah? We were also this, or I told you also what about the granodiorite, what intermediate igneous rocks are, what intrusive igneous rocks are, what a lava is, a mafic rock, a magma chamber, what is meant by magmatic differentiation, what an obsidian is, what a ophiolite suit is, what is meant by partial melting, what a pegmatite is, what a peridotite is, what a pluton is, what a porphyry is, and what a pumice is. I showed you also what a pyroclast is, a rhyolite, a sill, a stock, a tuff. We were also talking about ultramafic rocks, about veins, about the viscosity of a melt, about volcanic ash, and that was it for this PowerPoint presentation. And that was now the introduction into igneous petrology. And tomorrow, or I will give you, or will continue with the introduction in metamorphic petrology, and continue till the end of the week with the introduction in metamorphic petrology. And next week we will then go more in detail with igneous and metamorphic rocks. At the beginning we will talk more about or in the first half of the semester we will talk about the igneous rocks, and in the second half of the semester about the metamorphic rocks, and then we are done. So, and please answer all the short questions and send it to me for correction. Bye.